In this video, we're going to take a look at 3.7. I'm first going to walk you through the textbook and how the graphs lay out, because I think that's probably the biggest questions I've been getting, or the most questions. So here we have, this is section 3.7, 278 in the OpenStax workbook. So we have the arrow notation that we want to use to guide us through making graphs, and I will talk about this more. But if you're familiar with the parent functions here, so if we have 1 over x, the graph presents this way, like the one on the left. So you would have your arrows approaching in the opposite direction of the asymptote. So if here's my asymptote, my vertical asymptote is x equals 0, and I have this piece going downward, so it's decreasing, and then this other side is increasing, then I know I have a first degree down there. If I have a situation where they're approaching, each piece is approaching the asymptote in the same direction, in this case they're both increasing, then I would have it be squared. So whatever your binomial is. So when we look at more graphs in detail, I want you to think about that and maybe reference back to that page. Okay, so there's lots of good information in here about how that works and the graphs themselves, and you can kind of plot some points and see how they lay out. But it's really important to think about the parent functions as we graph new ones, or if you're given a graph and have to make the equation from that. So now you've already read through this section. Hopefully you've done that assignment first. So we're on page 282, and I just want to point out this definition here. A rational function is a function that can be written as the quotient of two polynomial functions, p of x and q of x. So that's just this. All this is a long way to say just it's a polynomial over a polynomial. Okay, so we're going to have things with exponents in the denominator. That's what makes it be rational. You've probably read through all this, and the domain of a rational includes all real numbers except those that cause the denominator to be 0. So we really need to exclude those and be careful, and that will be our vertical asymptotes, that we cannot have a point there. It's going to approach. So look at this one. If I have x squared minus 9 in a denominator, my asymptote I would have to look at would be right here. I could not have x equal to plus or minus 3. And so we would have, oh, well, we have an asymptote. But what's interesting about this one is we only have the asymptote here at x equals 3. Well, how come we don't have one at x equals negative 3? Well, look at this. If I'm to simplify this right here, x plus 3 over x plus 3 times x minus 3, and I would have a situation here where if I plugged in negative 3, I'm going to have 0 over 0. Anytime I have 0 over 0, that will be called a whole, or they have a fancy name for that. Also like a discontinuous thing, but whole at x equals negative 3, and you would have to plug that value in to find the corresponding y value for that. So anytime you have, so since at x equals negative 3 gives 0 over 0, so then therefore it's not also an asymptote. And I think that's what a lot of people do. They double it up, or they forget about the whole thing and just make it be an asymptote there, but it's not. It's going to be a whole. And if we plug our -3 in, and we have to plug it into our simplified version, so we plug it into 1 over x minus 3, because if we plug it back in here, we'll get undefined, right? So if I plug it in -3 minus 3, I would get 1 over -6, and that's this piece here. I'm going to blow it up for you. Okay, so right there we have a whole. So those are some things to look out for, and as we go through examples and you're doing your homework, that'll make much more sense. But we need to look into the graphs, and I think sometimes people gloss over that even when they're reading through and being careful, or it's just something hard to find and work with. So now I want you to keep that in mind as we go through the examples on the worksheet I gave you. So it's much more streamlined than the reading, so it is important to read through the book, but sometimes that's just really hard to understand. So we have a rational r of x equals p of x over q of x. P and q are polynomials. Local behavior, we want to look for all three of these things, but global behavior, we're just going to look for one. First, I want to just have you jot down again what a typical y equals 1 over x graph would look like. We would have our xy axis, and then the parent function here, we have horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. So we can kind of dash those in. Okay, so just keep those in mind. A lot of times we don't worry too much about the horizontal. There's no zeros on this one because it doesn't cross through or hit, because it's just the parent. We don't have any shifting happening. We also don't have any stretch or compress. It's just that way. No squares or other kind of powers in the denominator. Now if I have y equals 1 over x squared, like we saw in the textbook, but this is just like a really streamlined version here, we have this situation. So, you know, kind of reflects over the y-axis there. So it's approaching vertical asymptote is y equals 0. Again, horizontal asymptote is x equals, oops, I think I just reversed those. Let's switch that around. We have, well, that one was good. Y equals 0. This one should say x equals 0. There we go. Careful of that. So vertical asymptotes will always be x equals something, and horizontal will always be y equals something. So kind of glad that we can really point that out. Local behavior, again, we're going to look for all three of these. And a lot of times on a quiz or a test, I'll mark these out like with a line to put on the spot. Sometimes we have a whole and sometimes we don't. So you have to assess that situation. But definitely if there isn't one, write none. So I don't think you just didn't know the answer. So behavior, we're going to look at if it has a 0 at A0, if P of A equals 0 and Q of A is not equal to 0. So, and then we'll say like and or. Okay. Has vertical asymptote at x equals A if Q of A equals 0 and P of A is not equal to 0. And once I do the examples, you'll see more what this means. Has a whole at x equals A if P of A equals 0 and Q of A equals 0. So remember what I was saying when we have the 0 over 0, right? So for the whole, you would simplify it and then find the y coordinate by plugging into the equation after canceling out the common factor, just like I showed you before. So zeros, we're looking at numerator. For vertical asymptotes, we're looking at the denominator. When is that 0? And for wholes, we're looking for both, okay? Both numerator and denominator, okay? Because just to point out, it'll be 0. The whole fraction is equal to 0 if the numerator equals 0, okay? And if the denominator equals 0, the whole thing's undefined, and that's where our vertical asymptotes are. It's also undefined at 0 over 0, right? So global behavior, we're going to just look for 1. Sometimes people want to have more than that, but there'll just be one global behavior. Okay, so one thing to look for, if the degree of P is less than the degree of Q, then R has a horizontal asymptote at y equals 0. Okay, so for instance, if I have, the 1 over x situation, this numerator would be a degree of 0 and the denominator is a degree of 1. So then I'm going to have my horizontal asymptote going across at y equals 0, like I had with the parent functions. Because if the power, as it gets bigger and bigger in the bottom, it doesn't really matter if it's like a million in the top. If it's a million to the, just times 1, x to the 0 is times 1, the bottom is going to get bigger and bigger and bigger because it's raised to a power. Even if you have that same number but squared, it's going to approach 0, okay? Because as fractions, as the denominator gets larger, the fraction itself, the number itself, gets smaller and smaller. So if you have, if you have the degree of P is equal to Q, then R has a horizontal asymptote at y equals C over D. That's the coefficient, the lead coefficient. Because again, those, like say it's 3x squared over 2x squared, these will kind of approach the same thing, even though these differ a little. These will kind of be like 1. Alright, so you'll have 3 halves. Even if I had like 3x plus 2 over 2x squared, or 3x squared plus 2 over 2x squared, yeah, I would just look at the coefficient because this is pretty insignificant in the grand scheme of things when we're talking about really large numbers. What will dominate is this coefficient. Or the other situation that we might have is when the numerator, the degree of P, is greater than the degree of Q, the denominator. So then we need to use long division, and we're going to get an expression in the numerator left over, and that will be our slant asymptote. Now we are going to make this optional for this term, just because it's a very short term. A lot of times this is really easy to pick up later. So the professors that teach calculus are okay with that not being dove into too much in here. I'll touch on it, you'll learn about it, but if I test on it, it'll be like really lightly. And I won't include it on the final. It'd probably just be in homework and quiz, and if you're tight on time, you can just do a light version of that. Okay, so that's the intro for this. I hope that helps you get the big picture of it. It might not make sense till after you go through some examples and you might look back at that. But use this as a good checklist. You know, this is a checklist for all the pieces of the graphing. And in your electronic homework, you have to work the other way around too, like given a graph, find the equation. And that's kind of tricky. So I'll add in an example like that as well. But I'm going to just run through some of the pieces in the grunt work. I'm going to switch over to graph paper too. So if you have graph paper, that might be helpful for you to use. Have a great day.